All right, we're going to keep going with our work in linear functions, specifically working with scatter plots and trend lines. And here we're going to look at a challenge in a real-world connection. And I found some data. These are real data that I found online. So it's accurate, it's true, it's real data. And this data table shows you life expectancy for US women for birth years from 1980 up to 2005. So for US women born in these particular birth years, how long could they expect to live? And this is, I think, some good news. It shows that life expectancy is getting longer. Okay, so as time goes by, women in the US are expected to live longer. And I'm sure there's a lot of variability in these data with respect to geographic location or class or race or ethnicity. But as a whole, as a single group, looks like life expectancy is improving for US women. And so we have a couple tasks here. Our first task is to graph the data up on Desmos. And then we want to use Desmos to find a linear function of best fit and then make a prediction using our equation for the current year. So I'm filming this in 2020. So for a female baby born this year, what would her life expectancy be? Okay. So let's go ahead and go to Desmos real quick. And I've already typed the data in just to make things a little more efficient for this video. But if you were to type the data in on your own, you would go to this plus in the upper left and select table, and then just type in the X and the Y data. Additionally, what I've done is I've converted the X data to years since 1980. So let's go back to my note app real quick. So I converted these to year 0, 5, 10, etc. Okay, so easier to work with those smaller numbers. And then lastly, what you want to do, if you just, I'll go to a home zoom on Desmos real quick, and it goes from -10 to 10. You don't see any numbers, right? You don't see any data points. And so you need to work a little bit to find your data, okay? And get a good scale going and see if you can find your data and find a good scale that fills the screen with your data points. Okay, so it looks like our data are all in roughly a line, so that's good news. It would make sense to find a linear function to fit these data. So what I want to try to do is I'll show you how to fit a linear function to these data using Desmos, and then I'll take a screenshot of this and bring it back into my note-taking app, and then I can mark it up a little bit and show you some other things. So to get a line of best fit in Desmos, or any sort of a function of best fit in Desmos, let's add an expression. And the form you need to use is you're just going to type in the form of a linear equation that you want, but every time you see an x or a y, you need to write it as x1 or y1. And then lastly, instead of an equal sign, you'll use a little tilde. And these are all just kind of clues for Desmos to basically tell Desmos, hey, find a function of best fit for me. Don't just graph any old line for me. So let's go ahead and do that. And so I'm going to do y1 and then find my tilde, which is over in the bottom here, and then equal to m times x1 and then plus b. So and it found a line for us. So that's great news. I will take a screenshot of this and let's bring it back over to my note-taking app here. Okay, so let's paste this guy in. Cool, looks like we got it. And okay, so here's some things we can look at here. First of all, it's just, you should automatically just see, how does the line fit the data? And it looks like we did a really good job. Each point is basically right on the line, okay? So that's a really good fit. We call that a really good linear fit. And the other thing that tells us that we have a good fit is the R value right over in here. Okay, so remember from an earlier video, R can vary between -1 and 1, and the closer it is to -1 or 1, the stronger the fit. And here we have a really strong positive fit, so a positive correlation is what we would say. And this also gives us our parameters, our m and our b values. So it gives us our equation. And so we can really just write out the equation from that. We have y equals, I'm going to go to 3 decimal places just to get a little more precision, 77.424. Okay, so that's our equation that relates the year that a woman is born to her life expectancy. It's always, I think, helpful to think about what these numbers mean. So this number, the 77.4, really means at the beginning, or in our case, year 1980, because that's what we called year 0, a woman had a life expectancy of 77.4. And that agrees with our original data, right? It doesn't have to. We didn't force our line to go through that data point, but it's always nice when it does. It probably means that we have pretty good data. And then what does our slope mean? Our slope means that every year that goes by, a woman's life expectancy increases by about 0.11 or 0.12 years. So every year that goes by, a woman's life expectancy gets longer by, is that a month or 2? Okay. So let's actually answer the tasks we were supposed to answer here. Let's see here. Let's just clean things up a little bit. So we graphed the data, we got a function of best fit. Let's predict a life expectancy for a US woman born in 2020, okay? And we can really just plug in year 40, so this really means x equals 40. We can plug that into our equation. So y equals 0.115 times 40 plus 77.424. Okay, so go into a calculator for that guy. I get a life expectancy of 82.02 years. And that kind of makes sense. We would expect it to be longer than this 80 years because more time has gone by. So 82 years kind of makes sense here. Okay, that's a good place to stop right there.